Yeah, so this is the very bottom of a rocket. This is called the engine fairing. It's made of carbon fiber, and as you can see, it has multiple fins around it to stabilize the rocket. Inside there, we have something called a COTS solid motor. So COTS stands for commercial off the shelf. This is the casing for it. In here, we put solid propellants. They're ignited for the launch, and then in one run through, it goes all the way, burns, and launches our rocket up to 1,350 meters. As you can see, the motor is much smaller than the actual fairing. In general, our rocket is designed for way larger motors, so a much higher altitude can be reached, both from the size of the motor, but also from the forces the rocket can withstand. For us, the use of the small motor is really nice because we have to do less range safety. So to make a launch in Switzerland happen, which is obviously a very crowded area, we have to see that no one gets hit by the rocket and that we can be quite safe. So for this, we choose a mountain range, and there it just makes more sense for us to use a smaller motor because we can test all systems on this like 1.3 kilometers. And for us, the motor is not the interesting part in that sense, but it's of course what makes a rocket and what makes us be able to test all the systems and boost up. So as you can see, the fairing itself is quite light, so you can easily lift it up. Inside, you can see that there's like a lot of space there, and inside you have the motor retainer, which holds the engine in place so that the force can be distributed equally to the rocket, and that there's no wiggling, but the motor boosted up inside the rocket and takes rocket with it. Okay, so right on top of our engine fairing sits this right here. This down here is the air brake section, and up here you can see our avionics stack. The air brakes, as you can see, are those metal plates which are around the rocket. Up here is the motor of the air brakes. It's an electric motor which can be controlled by the avionics stack up here. And what it does is it extends the air brakes outside symmetrically, which is relevant for safety reasons, but it extends them outside of the rocket, so the drag coefficient of the rocket itself is drastically increased. The air basically comes, goes, hits the plate and breaks off. And as you can imagine, like on cars or something, or planes, it drastically slows down the rocket. For us, we use it in the coasting phase. So as soon as the motor's off, the motor goes up. As soon as the motor is burned through, we have a coasting phase, which is actually quite long. And in this coasting phase, we can deploy the air brakes and adjust it in live based on the data we have on velocity, on GPS tracking. All of this goes into play, and the rocket calculates how much those air brakes have to be extended. And with this, it enables us to hit a very precise altitude. So we choose a motor which is slightly stronger than what we want to achieve from the altitude. And then with this, we slow ourselves down to the targeted apogee. Up here is, as I said, the avionics stack. It's a modular design, so you have multiple PCB, which stands for printed circuit boards, which is commonly used for computer science or just computers in general. And we have multiple here. They all have a different function, so they're always regarding one system. We have one for recovery, we have one for air brakes. All of this, and it comes together and it steers the rocket. It's really the brain of the rocket, where all data comes together. And yeah, also relevant for us. In general, you can see we have multiple couplers between the fairings, but especially the one below the avionics stack is especially relevant. So we have 2 slots on each side for a camera and one for the power supply. And we also have multiple holes here for wind measurements. So it's pressure sensors, which then calculate the wind which comes onto the rocket. Basically, this one is where we get a lot of data from. It sits directly next to the avionics stack, which makes sense in that regard. But yeah, we use the data to guide the rocket. Yes, as you can see from the inside, this fairing looks a little bit different. It's made of fiberglass instead of carbon fiber, and it sits here on top of the avionics stack. We choose fiberglass, although it's a little bit less strong, so we need a lot more layers and makes it a little bit heavier than the carbon fiber. but carbon fiber stops electromagnetic waves from passing through, not 100%, but to some extent, and to ensure a stable connection between the rocket and the ground station, we chose fairing like this. So all data can go through and we have a constant communication without any interruptions. Yes, and here we come really to the heart of the rocket, so our core system. It sits on the very top, only the nose cone is above it. And what we have here is, as you can see, a big parachute, or to be exact, 2 parachutes. They are housed inside here. This is the parachute fairing. And we have the big one, which is packed inside there normally, in this packing here. And then we have the small drogue chute, which is deployed earlier. And how it works is the rocket goes to apogee, and then the nose cone is cut off. We can show that later. And with this, first the drogue chute comes out. This is a smaller chute which is round, so it can't be steered or anything, but it slows the rocket down to a critical velocity of 30 meters per second. So this is the maximum speed. No matter how long you fall, you will always only have 30 meters per second. This is what this drogue chute does. And then as soon as we hit the altitude of 800 meters above ground, this chute here comes out. It is deployed inside here. And this one is much larger. It's a so-called ram air parachute. So it's something you would use, for example, for paragliding or just in general skydiving. You can see it has a lot more lines, a lot bigger than the one below. And this one has a critical velocity in the z-axis of only 5 meters per second, which enables us that the rocket, when it hits the ground, is on a slow enough speed so that it's fully functioning afterwards. It can be steered, and that's really what we try to design here, using this electric motor. So if 2 electric motors, which the person, when you steer it yourself, this is basically the pendant to that. So we have, once again, our avionics stack who steers it, takes all the data in, and it has a rough pattern that we pre-calibrate. So it basically comes down to having imaginary walls, which he tries to go around in. And inside those, the rocket steers itself down using those lines to steer the parachute, with the rocket hanging onto it and going around the lines and then going to one targeted location, so that we can recover it there. So we don't just shoot it somewhere and try to recover it anywhere, but we try to hit a point where we can then safely land the rocket and recover it completely. Yeah, so now at the very top of our rocket, we have the nose cone. It is attached to this mechanical separation mechanism. This mechanical separation mechanism would sit inside the parachute fairing we've just seen. It is locked using those bolts, so they are extended outside into the parachute fairing. And here we have springs which are preloaded. So at the end it sits here, the fairing sits on top, and it's loaded by springs. And then we have lines going around here, those are called dynamers. Those hold it in place so that the springs are on tension. And then as soon as the avionics stack detects the apogee of the rocket, zero velocity in the z direction, it detects the apogee, and then a heat cartridge is activated. So it's just a lot of current going through a junction, and this heats up very fast and up to 400 degrees. And then it melts the dyneema in around 2 seconds after the apogee is detected. And with this dyneema melted, the springs can now extend, and they extend here. So this system, as well as the nose cone, are shot out then. So this whole attachment goes outside the rocket. It is still attached using a rope, so it is fully recovered as well. But now the parachute can come out. And inside the nose cone we have can sets, which is the purpose of the rocket in that sense. So it's a sounding rocket, so we want to do scientific measurements inside the atmosphere, so suborbital flights. And for this we have 2 can sets which we actually will fly. We have one developed by a student and another one developed by a Spanish student team. And those sit inside the nose cone here and can conduct measurements during the launch.